All right, hello everyone. I'm Michał. I work at MUI at a little component library called BaseUI. Has anyone used it before? I see a couple of hands. Good, good. So over the past year, as we've been preparing BaseUI's first stable release, a big part of our work, performance improvement, we profiled our components asking why is this slow. Sometimes it turned out it was something stupid I wrote a month earlier. But sometimes we discovered some patterns that were degrading performance. So today, I want to share the problems we discovered and the solutions we applied to fix them. So every single example from this talk comes from an actual problem we found and fixed in BaseUI. So how do we make a component or a whole website faster? It's very simple. Just throw less at the CPU, and this could be the end of this talk. But what does it mean exactly? What does less work actually look like in React? It comes down to a couple of things, and this is not an exhaustive list, just a couple of things I thought are pretty important to cover in these 20-something minutes. So first of all, reduce the number of renders. React renders are fast. But you know what's even faster? Not having to render. If you have to, reduce the amount of work done within the render. When a component must render, make sure it's not doing any more than it needs to. And this includes reducing memory allocations or optimizing DOM operations. Now, you might be thinking, I'm building an application, not the UI component library. Does this apply to me? And the answer is yes. When you're building a library, the stakes are higher. Our code runs inside someone else's app alongside their components, their state management. So every millisecond our library spends on rendering is a millisecond that application developers have less to, is a millisecond taken from their budget. So we have to be very efficient because we need to leave room for the code that actually makes the product. But the patterns themselves are the same patterns that make any React app faster. OK, let's start with a common performance problem in React, re-rendering things that didn't change. So here we have a list of items, songs in this case, each with a favorite toggle. We store the checked state somewhere near the root app component and pass it down via context. When a user toggles an item, every single item re-renders. The moment the context value changes, React has to re-render every component that subscribes to it. So memo can't really help here because it works with props, not with context. And we hit exactly this problem in BaseUI when building our select component. When users hover over an option, we update a highlighted item value in the root component context. But updating this context on every hover means every single option of the select re-renders, even though only two of them actually changed, the one that has been highlighted before and the one that's highlighted now. So one way to solve this issue is to split the context-dependent component into two. A thin wrapper that just subscribes to the context and reads the value, and a richer one that accepts this context value as a prop and can handle more expensive rendering. So how does it help exactly? Here's how it can look like. The song component reads the favorites array or set from the context and generates isFavorite, a Boolean saying whether this particular song is in favorites. This computed value is then passed as a prop to the inner component I called songDisplay, which means we can use React memo on it to prevent it from re-rendering. So now, on every context update, React will re-render the thin song wrappers, which should be super quick, those two songDisplay components. This works, and actually, it's a solution we implemented in our components, but has some drawbacks. React still needs to render these wrappers basically every time the context changes. And we're introducing another component to the tree. It also doesn't look very nice to have this logic split. So can we do better? We can, and we did. We introduced a store to keep our data. So a store is basically an object that holds some state and is able to notify its listeners when the state is changed. These listeners can run functions called selectors to determine if a particular slice of state changed and only trigger a re-render when it does. So in our case, the song component can observe just the isFavorite state that's calculated specifically for it. How does it look? It kind of depends on the implementation, because there's no one canonical store implementation. I'll show you an example of what we did, because we wrote our own implementation for base UI. So the store instance, it's initialized somewhere. Could be even outside of React components, but can be within a component and then shared with the rest of the application with a context. It's safe to do so in a context because when updated, the store instance doesn't change. The reference stays the same, kind of like a ref. In its arguments, we set the initial state and define the selectors. In this case, just one is favorite. The selector is a pure function that accepts state, and in this case, song ID used to determine if this song is favorite. Then we have the useState method that accepts the name of the selector and its arguments. This is how we implemented it. It subscribes to the store, runs the selector, and it changes. It retriggers a re-render only if the value returned from the selector changed. So we created our custom implementation to suit our needs exactly, and to not to introduce any additional overhead that we don't need. But in your applications, you can use libraries that provide a store like Zustand, for example. If you'd like to dig deeper and create your own, to understand how it works, you can take a look at our implementation on GitHub. It's pretty minimal, but powerful enough to power our components. The secret glue between the store and React code is React's useSyncExternal store hook. As the name suggests, it synchronizes the state coming from an external store to React world, triggering a re-render whenever this external store is updated. And external in this context doesn't mean like living on a remote computer over the network. It's external to React code. Now we did some more crazy things to optimize the store even further, combining multiple subscriptions into one, while formally breaking the rules of React, but then thoroughly testing that everything still works correctly. I wouldn't recommend this for all applications, but if you're interested in seeing what's possible, look for fast hooks in our code base. So after these changes, you can see that toggling the favorite state of one song doesn't re-render the others anymore. Okay, let's move on. Sometimes we can make an application faster by rethinking and redesigning its architecture or patterns. So let's get back to our song list example. It's safe to assume that icon buttons like these will have tooltips. And traditionally, in libraries like Base UI, Radix, and many others, you define tooltips like this. There's a root part that wires together a trigger and a pop-up. And in our case, a pop-up is made of a portal, positioner, and a couple of other parts. For closed tooltips, we don't render anything below portal. But still, in an application where no tooltips are open, React has to create and render these roots, context providers, and portals for each row. So this looks quite inefficient, especially that if you consider that you can have only one tooltip open at a time. So wouldn't it be nice if we could define all these common parts just once, closer to the root of the application? So a song component could have just the trigger, and all these triggers could reuse the same pop-up. So the first problem that arises here is what should be the content of the pop-up? How do we know whether to show add to favorites or remove from favorites? Or what if the content of the tooltip is like entirely dynamic and, for example, have the name of the song in it? We solve this with the payload prop, and whatever is set as payload of the trigger used to open the tooltip can be read from within the root part. In our case, payload is an object with the isFavorite field, although even a Boolean would do in this case. We read this value inside the tooltip root and decide what text to render. Okay, but then how do these parts communicate together? And is it type safe? If I have an object with a Boolean field in the triggers payload, how do we ensure the same object shape in the root? So our solution to this is a handle prop that wires together all the parts of the tooltip. A handle is an object with a stable reference that can be defined in a module scope, kind of similar to the store because really it's a wrapper around a store. It's passed to all components that need to communicate. It's kind of like an explicit, strongly typed React context. And because it's strongly typed, we can ensure that the type of payload is consistent between parts of the component. We call this detached triggers, and BaseUI supports it not just for tooltips, but for menus, popovers, dialogues, and preview cards. And in our tests, we found out that it improves the initial mount time by over 50%. Now, there's one other bonus feature that detached triggers enable, and let me show you an example with popover. Since the shell of the popover is shared, it reuses the same DOM node for all pop-ups, and just the contents change, we can basically animate content transitions between triggers. So this pattern not only improves performance, but also enables some better UX. Okay, wasn't React compiler supposed to solve all the re-rendering problem without any additional work from developers? Well, yes, it does, but it also kind of depends. So for us, it didn't really help a lot. We tested it some time ago, and we haven't seen impressive speed up. We're kind of already aware what should be memoized and what shouldn't. And for example, the compiler insisted on memoizing data that we knew changed every render. So basically, any additional code around it is just a waste of resources. But the biggest drawback was an increase in bundle size. So with React compiler, our library grew by 26%. So this basically wasn't acceptable for us. But I'm not saying React compiler is bad. Try it out, see if it helps in your cases. Maybe you'll see some better speedups. Maybe you don't care so much about bundle size, and decide for yourself. All right, we've talked about reducing the number of renders. Now let's talk about what happens inside a render, and let's start with the cost of memory allocations. And by the way, this section is useful whether you use React or not. So if there are any hidden Angular fans in the audience, or maybe someone still using jQuery, this is for you too. JavaScript doesn't really care what framework allocated garbage. So every time you create an object, array, or a function in JavaScript, that's a memory allocation. And every allocation is essentially work for the garbage collector. One allocation is cheap, but they add up. And to be clear, I would categorize these kinds of problems as micro-optimizations. It's unlikely that you'll see major improvements by this alone, unless you're doing something really terrible. But still, it's good to remember this when writing code, because this can be almost applied automatically. It doesn't cost you anything and can make applications slightly faster. Starting with something really straightforward. If you have a value that doesn't change between renders, define it outside the component in module scope. This applies to functions as well. So unless the function depends on data from the component, you can move it outside. This will reduce allocations and stabilize this function's reference, so you can possibly eliminate use callbacks. If you work with immutable data structures, consider creating common constants for empty arrays, objects, or no-op functions. In this particular example, like object freeze is used as an extra safety measure to ensure nothing accidentally mutates this shared instance. So this can be defined like globally per application. Functions like map, filter, for each are usually clean and readable, maybe except for some more nasty cases of reduce that require much more brain power to process. But each one of these calls takes a callback function, and each callback is an allocation. And these functions are usually also a bit slower than just having a for loop. I'm not saying don't ever use map, for example, but when like performance is key, when you have like a really hot path, reach for a for loop instead. And these were just a couple of examples of patterns that may not give you huge performance gains, but are relatively cheap to introduce. You can just remember them when writing code, or more likely teach your AI agent to remember them when writing your code. Let's move on to something that can have a bigger impact, and this is DOM operations. So there are cases where you need to manipulate the DOM directly, like measure something, position something. It may be not very common in like line of business applications, but very common in like graphics apps, games, and UI libraries. So what can go slow here? We got like 5 minutes left, so let me teach you how web browsers work. In order to render a page on the screen, browsers have to do several operations. Apply the CSS styles, figure out where the elements are and how big they are, paint the actual pixels, and so on. It's basically a waterfall. But it's a smart waterfall. When you modify the DOM in your JavaScript code, say change an element's width, the browser doesn't immediately recalculate layout. It marks the layout as dirty and defers the work. So if there's another write operation to the DOM in the same script that could invalidate this calculated layout, it's smarter to just wait until the script finishes to do all this work. But the moment you read the layout property, like, I don't know, offset height or get bounding client rect, the browser has to flush that deferred work to give you an accurate answer. And this is called forced synchronous layout or forced reflow, and you should avoid it if possible. But there's something worse than a forced reflow, multiple forced reflows. If your code alternates between the writes and reads from the DOM, you're forcing the browser to recalculate layout on every single iteration, and that makes it super slow. This is called layout thrashing. And the fix here is to batch. Do all your reads together and all your writes together. This is how it looks in the profiler. You can see multiple calls to offset height triggering style recalculation. And if you click on the recalculate style block, you'll be able to see an arrow pointing to a method or a property that triggered this style recalculation. It might be a bit counterintuitive, but setting the style is not the slow part. Reading it after you change it is the slow part. By the way, the Chrome DevTools has an insights panel that help you find cases of performance issues like this. Okay, so some of these patterns you can just apply automatically when writing code, reducing allocations, batching DOM operations. Others need more work to discover, like detecting unnecessary renders or discovering suboptimal patterns. But the bottom line is performance is a feature. Think about it, improve it, and your users will be happier. I'm Michał Dudak. Thank you very much. I'll be around if you want to talk about base UI, performance, or anything. Thank you.